Hello and welcome back. So today I want to continue talking about phase lock loops by looking at another fundamental building block, the VCO or voltage controlled oscillator. So what I want to do today is look at the two fundamental types of oscillators used as VCOs, the harmonic oscillators and the relaxation oscillators. So what I want to do is look at how these work, what are the basic principles behind them, and also see how their frequency can be controlled using an external control voltage. So if you're curious, then keep watching. So let's start things off with looking at what an oscillator is supposed to do. Well, it's supposed to oscillate. But in other words, what that means is that it's supposed to provide an output signal which should be periodic, so either a triangle, a square, or a sine wave. And this should be achieved after supplying the circuit with a DC supply. So in other words, it's basically a DC to AC converter. Now, the first type of oscillator to look at is the harmonic or the linear oscillator. So this circuit is commonly built with an amplifier and a feedback network that has a selective response. So this system should only have a positive feedback at a specific frequency dictated by the feedback network. Therefore, the feedback network is commonly implemented as a filter. So this can be an RC filter or an LC filter. So usually at lower frequencies you have the RC version, at higher frequencies the LC version. And the output frequency therefore is the resonance frequency of this filter. So to change the output frequency, we need to change one of the elements of the filter. Most commonly, the capacitor is the one that is being varied. And an easy way to make a voltage-dependent variable capacitor is by using a varicap or varactor diode. Now, one way this can be implemented is in a Colpitts type oscillator. So what I have here is the oscillator. So we have our amplifying element, a transistor, and then a feedback network built with an inductor and a capacitor. And in parallel with these, we also have our varicap diodes to provide the extra voltage-dependent capacity. And to change the value of these, I'm inserting a voltage that goes from 0 to 5 volts and back. So we can see the frequency increase and decrease. Then I also added an isolation stage, so this is just a small amplifier that isolates the output from the oscillator so that whatever happens on the output doesn't influence the oscillator. And well, to compare this, I have the exact same circuit, but here the signal voltage is 0. So to see what the applied voltage actually does to the frequency. So if we run this thing and we look at the fixed frequency, but also the VCO output. Now at this point it's not very clear, but we can turn to an FFT plot to see more clearly what happened. And if we do this and zoom in a bit, well, we can see our fixed frequency oscillator has, well, a fixed frequency. It's around 517 kilohertz, but our VCO, our voltage controlled oscillator, has a frequency spanning from about 518 up to 570 kilohertz. So it's not a very big variation, but that has to do with the capacity variation of the varicap and the other capacitor already in the LC circuit. So you can have much wider variations with the appropriate components. Now, let's turn to the other major type of oscillator used in voltage-controlled oscillators, the relaxation oscillator, which is also called a nonlinear oscillator. Now, what this means is that unlike the linear oscillator, with the nonlinear oscillator, you can't get any sort of output value. So for example, you can't create a sine wave. Relaxation oscillators are known for being able to create square or triangle waves. So to see how this works, I prepared this block diagram. So we still have a signal loop, but rather than having an analog amplifier, we have a digital amplifier, which can output two digital states, so a 0 logic and a 1 logic. Then this gets passed into a storage element, which charges and discharges based on this output value, and then based on the voltage on this element, the circuit switches. So we can get our square wave output if we look directly on the output of the amplifier, or we can get a triangle wave if we look on the storage element. So usually the charging and discharging profile of this element will look like a triangle wave. And now we can use both capacitors or inductors as storage elements, but most commonly a capacitor is used. Now the way in which you go from your square wave to your triangle wave is by adding a current limiting element. So usually this is a fixed value resistor. But the way in which you turn this sort of oscillator from a fixed frequency oscillator into a variable frequency oscillator, which can have voltage control, is by swapping this fixed value resistor with a current source, current sink system. So you can very easily set the output value of a current source or a current sink using an external voltage. And you can use that to charge and discharge your storage element and then close the loop. So to understand how this sort of oscillator works, I prepared this basic example using the classic 555 IC. So what I got here is, well, an oscillator. So it's one of the simplest oscillators that you can build with this sort of IC, in which we're charging the C2 capacitor through a fixed value resistor. This thing is compared internally, and then it's periodically discharged using the discharge pin. So if we look on the voltage on this capacitor, we can see it charging and then suddenly discharging, and we can also see the corresponding square wave output. So this isn't a 50% duty cycle output, but it's a square wave. The main reason why the pulses are so short is because of the short discharge time. So if both the charging and discharging currents would have been equal, then we would have gotten a 50% duty cycle. Like this, we get a slightly smaller duty cycle. But anyway, now let's turn the circuit into a voltage controlled oscillator. And for that, we can replace our resistor with a programmable current source. And quite an easy way to do that looks something like this. So what I have here is a current mirror. Basically, this will take whatever current is on the right side and supply it on the left side. So this can be used to charge the capacitor. And then the current can be set by applying a voltage through a resistor. So our positive voltage supply is 5 volts set by the supply of the circuit. We will have about 0.7 volts drop on the transistors. And then depending on what control voltage we're applying, we'll have a certain current going through this fixed value resistor. And now we can mirror this current onto the left side. So if we simulate this circuit, so first of all, this is the applied voltage, so it goes from 0 to 3 volts. And we can also see the current, which goes from a maximum value when we have the largest voltage drop to a minimal value when we have the smallest voltage drop. And we can also look at the VCO's output. So let me just separate these. And now even without measuring, we can already see that there's a frequency variation. So you can see here on the left side that all the pulses are quite close together, whereas on the right side, they are far more spread apart. So when we had the maximum current here on the left side, we were charging the capacitor really fast, so we had a high frequency, whereas on the right side, currents were much smaller, so the charging time took much longer. Now, by increasing the simulation time and also editing this pulse voltage to go up and down, we can also see what the output spectrum of this sort of oscillator looks like. And we can, of course, compare it to the fixed frequency oscillator. So if we zoom in a bit into this, we can see that the VCO's output is quite a blur, and that's because of the large frequency variation. But another thing that's important to mention is that since this is a square wave, we have a lot of harmonics. So you can clearly see the harmonics in the fixed frequency oscillator. And well, when we're varying the output frequency of our VCO, we're also varying the frequency of the harmonics. So that's the main reason why this area here looks like such a blur. Now, the main problem with the circuit is that even though it's a voltage controlled oscillator, it doesn't really output a 50% duty cycle square wave. Now, you can fix that by either adding a divide by 2 circuit at the end of it, or by replacing the whole thing with a slightly more complicated circuit. One example of this can be found in the CD4046's datasheet. So if we go through this document, we'll find the voltage controlled oscillator section, and basically what we have here is our capacitor, which is an external component that is being charged and discharged. Whether it's charged or discharged is set through this H bridge, so with transistors N2, P4, P5, and N3, and then we have a state machine that switches between charge and discharge. Now, to turn this into a voltage-controlled oscillator, the charging and discharging current goes through a current mirror and is set through the VCO's input. So again, we're setting a certain current through a resistor, and this is then mirrored through the current mirror. And this sort of circuit will output your 50% duty cycle. So now, the last thing to do is to see how these two types of oscillators work in real life. And for that, I prepared the setup right here. So what I got here is a board that has both the harmonic oscillator and the relaxation oscillator, and I will be testing them both one by one. And well, to test them out, I have one of the channels of my oscilloscope, the blue one, connected to my signal generator, which is connected to the VCO's input, so to the control signal, and then the yellow channel is connected to the oscillator's output. So we can see at the same time how the frequency varies based on the input voltage. So right now we see that we have about 480-490 kilohertz on the output, and our input voltage is static. So now if I turn on the generator, I have a triangle wave being applied, the period is 2 seconds, and the amplitude is 5 volts, so it goes from 0 to 5 volts. And we can see that here in blue, and at the same time we can see in yellow our output frequency varying. So even if it's not a very big variation, we do see that our waveform is changing. We could get a better view of this if we turn to an FFT spectrum. So what I have here is a zoom in on our output frequency, and I set my two cursors so that the signal goes in between these, and well, it goes between 470 and 510 kilohertz. So not a big variation, but in certain cases this can be enough. And of course this can be improved by using different components in the oscillator or with different types of varicap diodes. So now let's turn to the other circuit, to the relaxation oscillator. So first of all, this is the oscillator built with the 555 with the simple current mirror. And if we look at the waveforms, well, we can see the output being almost a square wave, so it's not completely perfect, but it's good enough for our experiment. And again, with a fixed input into the circuit from the signal generator, nothing is happening. But if we change that, if we apply the same triangle wave, we see that we have quite a substantial variation in frequency. So because of the large variation in current that can be achieved, we have a large variation in frequency. Now we can also see the frequency variation in an FFT spectrum. So what we can see here is our fundamental frequency varying up to about 73 kilohertz. And at the same time we can also see all of the harmonics varying in sync with it. So this is the typical spectrum you would get from a square wave. So all in all, depending on what your needs are, you can go for either harmonic type oscillators if you want sine waves at the outputs of your VCO and of your PLL in general, or you can go with relaxation oscillators, so if you're working with square waves in digital circuits. So both of these types of circuits are widely used. And all in all, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.